Hello everyone, in this video we'll be going over the net change theorem. So in the last videos we talked about the net signed area. So recall the net signed area. And what we said was that the definite integral accounts for areas above the x-axis as positive and areas below the x-axis as negative. And this is actually really beneficial for applications. By accounting for negative change. For example, if f of x represents profit, right, the integrand, then the integral actually accounts for losses. The net change theorem which says the new value of a changing quantity equals the initial value plus the integral of the rate of change. Right, so basically at time B, the amount that is present is the amount that was present at time A plus the change that occurred from time A to time B. And we use the rate of change function, right? So if we want to know, equivalently, if we want to know what the change was from time A to time B, right, we just do the integral of the function. Right, these are equivalent formulas. I literally just subtracted this over here. So it depends on what exactly you want to know. But remember that net change accounts for the negative quantities by default because, as we saw before, net signed area, which was the default way we integrated, accounted for negative areas. So let's do an example. So given a velocity function v of t equals to 3t minus 5 in meters per second for a particle in motion from time t equals 0 to time t equals 3. Find the net displacement. So whenever you see net, you already know that means that we want to account for negative distance traveled. Right, so we want to just do the integral from 0 to 3 of 3t minus 5 dt. Right, so we just do the antiderivative, which, remember, we can just leave this 3 here, constant multiples, and that becomes 3t squared over 2 minus 5t, and then we have to plug in the bounds. So we end up with 3 times 3 squared all over 2 minus 5t minus 3 times 0 over 2 minus 5 times 0, which are both gonna become 0. Right, anything multiplied by 0 is 0. So 9 times 3, that's 27 over 2. And whoops, I forgot to plug in my 3 here. Oop. So that becomes minus 15, or I'm going to simplify it to minus 30 over 2. So I have a common denominator, and then I know this is negative 3 over 2. Right, and that is going to be meters, right, is for the displacement over that time period. So in the end, accounting for positive distance, so distance in one direction and the distance back, what's left was negative 3 over 2 meters. So the next part is going to be find the total distance traveled. And remember, for total area, we need to do the absolute value of the function. So we need to do the integral from 0 to 3 of the absolute value of 3t minus 5 dt. So the first thing that we're going to have to do is figure out when is this function positive and when is it negative. Because when it's negative, we're going to want to pull out the negative sign. So what we do is we take the equation in here, and we set that equal to 0, and we solve for t. Because this is, remember, to go from positive to negative or negative to positive, you have to cross 0. So this is going to tell us where it switches to negative or where it switches from negative to positive, right? So we add 5 to both sides, and then we divide by 3. So at time 5 over 3, I know that's where I need to split this interval up into 2 intervals. And then I think about when is it positive and when is it negative. Well, when t is 2, this whole thing becomes 6, and 6 minus 5 is when it's positive. So I'm gonna assume, right, and 2 is 6 over 3. So I know everything greater than 5 over 3, because 2 is greater than 5 over 3, is gonna give me a positive output. And then that means that, right, that makes sense. So anything less than 5 over 3, right, because 5 would make this smaller than 5. So when I subtract 5, it ends up being negative. Okay, so this part is where it's negative, right? And remember, our original was from 0 to 3. So we have on 0 to 5 over 3, the absolute value of v of t, right, it's negative. So we have to multiply it by negative to make it come out positive. And then from 5/3 to 3, we know that v of t itself, right, is positive. So we don't have to multiply it by anything. It's automatically positive. Okay. So this means that what we're doing is we're splitting up our integral into 2. So we have 0 to 5/3, and that's going to be negative, and that was 3t minus 5. Plus, I'm going to have to make this smaller to have enough space. The integral from 5/3 to 3 of the original function. And then we just do this. So for the first integral, right, we're going to have to end up distributing. So that's going to become 0 to 5/3, right? So we distribute this to both terms. So it becomes positive 5 and a negative 3t. And then this one stays the same. So we can actually, well, I'll integrate it all in the next step, I guess. Just bring this down. And then now I'm going to integrate. So this becomes 5t minus 3t squared over 2 at 0 and 5/3 plus 3t squared over 2 minus 5t at 5/3 and 3. So then we plug in everything. So 5 times 5/3 minus 3 times 5/3 squared all over 2. And then minus, all of that would be 0, right? When I plug in 0 into here and into here, it's both 0. So then I plug in 3. And then I have to subtract from that, plugging in 5/3. Okay. So then, right, this becomes 25 over 3, and then this becomes 25 over 3 times 3. That's going to be 75 over 3 times, no, 75 over 9. And then that's going to cancel 75 over 3 again. Okay, so do all the math. 27 over 2 minus 15 minus 75 over 18 minus 25 over 3. Right, and then I simplify all of that and I end up with 41 over 6 meters. So you can see that this is a much larger number than this, right? Because here we're counting for all the change as positive. Like we didn't care if we went reverse or forward or right, anything we did was accounted for, versus here the negative was accounted for.